So what really makes chemistry happen? You know, below the surface of all the mixing and reacting, there's this hidden world of just furious activity. Today, we're going to pull back that curtain and look at the two fundamental blueprints that electrons follow, one for reacting on demand, and the other for building permanent stability. Okay, let's dive right in. You know, we all learn about molecules with those simple ball and stick models, right? They make everything look so rigid and static. But the reality is, a molecule is an incredibly complex piece of architecture. Think of it like a building. See that framework in orange? That's your strong, stable sigma framework. It's like the steel skeleton holding the whole thing together. But then you've got these dynamic pi systems, those electrons in the double bonds. They're more like the building's electrical wiring, ready to carry a current and make things happen. It's this hidden constant motion that dictates, well, everything.
So how do we even begin to make sense of this controlled chaos? Well, it turns out this whole electron dance isn't random at all. It actually follows two fundamental sets of architectural plans. Let's take a look. On this slide, we get to meet the two main characters in our story today. Over on the left, we have the electromeric effect. Think of this as a temporary, pretty dramatic shift of electrons that only happens when another molecule, a reagent, comes knocking. And on the right, we've got hyperconjugation. This one's a permanent, structural feature that provides constant, built-in stability. So one is an active response, and the other is just a passive state of being. All right, let's start that active response. You can think of the electromeric effect as the molecule's on-demand reaction system. It's normally just sitting there dormant, but it springs to life the second it's needed. Let's really break this definition down. The key phrase to lock onto here is complete transfer. We are not talking about some gentle tug of war. Nope. This is one atom completely snatching a pair of pi electrons, which happen to be the most mobile electrons in the molecule. But maybe the most important part is the trigger. This only happens when another molecule, an attacking reagent, shows up. It is a purely reactive state. And this slide, it gives us the perfect analogy. Up at the top, you've got a stable molecule, everything's fine. The light switches off. But then a reagent arrives. It could be an electrophile looking for electrons, the E+, or a nucleophile with electrons to share, the nu-, and suddenly there's a demand. And boom, the pi electrons shift completely, creating a positive and a negative charge inside the molecule. The light is officially on. But, and this is crucial, as soon as that reagent is removed, the effect just vanishes. It snaps right back to its original state. Purely temporary. So this slide shows us the first type. We call it the positive or plus E effect. I want you to watch that curved red arrow. When the attacking reagent, in this case an H+ ion, gets close, the pi electrons from that double bond move directly to the carbon that the reagent is about to attach to. This totally paves the way, allowing that new bond to form. And here is the exact opposite scenario, the negative or minus E effect. Look closely at this one. The attacking reagent, a Cn- ion, attaches to one of the carbons. But this time, the pi electrons flee in the opposite direction. They move over to the other carbon atom. So with the minus E effect, the electrons are always moving away from the point of attack. So just how powerful is this temporary effect? Well, this seesaw right here is a perfect illustration. The electromeric effect is an active, immediate response to a threat or an opportunity. Other effects, like the inductive effect, are more like passive structural pulls. When you pit them against each other, the active, on-demand electromeric effect is going to win that fight almost every single time. It dominates the outcome. Okay, so let's shift gears. We've talked about the reactive side of things. Now let's get into the structural side. If the electromeric effect is the molecule's temporary reaction system, then hyperconjugation is its permanent, internal steel frame, providing constant, unwavering stability. Hyperconjugation is this permanent stabilizing force. It happens when you have a very specific arrangement, an alkyl group. That's just a group of carbons and hydrogens attached right next to what we call an unsaturated system. All that means is a part of the molecule with double bonds or maybe a positive charge, basically a place that's hungry for more electrons. This effect lets electrons from those sturdy sigma bonds spread out and help stabilize that hungry spot. Okay, here's how it actually works on the orbital level. We've got a carbocation, that's a carbon with a positive charge, which means it has an empty p orbital. You can think of it like an empty pocket. Well, the electrons from a neighboring carbon-hydrogen sigma bond can actually overlap with this empty pocket, sharing their electron density. This process, called delocalization, spreads that positive charge out over a larger area, which in chemistry is a very, very stabilizing thing.
So this brings us to the crucial takeaway. The more of these helpful neighboring CH bonds you have, the more stable the whole molecule becomes. It's pretty straightforward. Just look at the progression on the slide. In step 1, the ethyl cation has 3 of those adjacent CH bonds to help out. In step 2, the isopropyl cation has 6. And finally, in step 3, the tert-butyl cation has a whopping 9. This directly explains why that tert-butyl cation is the most stable of the 3. It simply has the most hyperconjugation going on. You know, this stabilizing effect is so unique, it's even earned a special name, no bond resonance. And it gets that name because if you could freeze time and look at one of its resonance structures, it would look like a hydrogen atom has kind of lent its electrons to the cause and is just hovering there, held in place by that shared electron cloud, instead of a direct formal bond. It's a bond that exists without really being a traditional bond. Pretty cool, huh? Okay, so we've seen the reactive, on-demand effect, and we've seen the constant, structural one. Let's put them side by side and create a nice, clear diagnostic chart to really nail this down. This matrix sums it all up perfectly. Let's just walk through it real quick. First, the state. Electromeric is temporary. It goes away without a reagent. Hyperconjugation is permanent. It's always on. Next up, the trigger. The electromeric effect is external. It's caused by an attacker. Hyperconjugation is internal. It's just part of the molecule's own structure. What about the electrons involved? Electromeric uses those mobile pi electrons from multiple bonds. Hyperconjugation uses the sturdy sigma electrons from adjacent CH bonds. And finally, the primary result? The electromeric effect gets a molecule ready for a reaction. Hyperconjugation is all about dispersing charge and providing that inherent built-in stability. So, what's the big payoff here? Why does it matter so much to be able to tell these two effects apart? Well, it's because they are literally the traffic cops directing chemical reactions. This is the ultimate takeaway. This is the whole ball game. The way electron density gets moved around inside a molecule, whether it's from the temporary jolt of the electromeric effect or the permanent stability from hyperconjugation, determines everything. It dictates if a molecule is going to undergo a substitution, an addition, an elimination, or a rearrangement. These electron dynamics are the cause, and the reaction type you get is the effect. And that's the real power of this knowledge. See, chemistry isn't just about mixing stuff together and hoping for the best. By understanding these fundamental rules of electron dynamics, chemists can look at a molecule's structure and predict with amazing accuracy how it's going to react. They can design experiments to favor one pathway over another, literally controlling chemical outcomes with incredible precision. So, where does this all leave us? We've seen the rules that govern this secret world, the temporary shifts and the permanent supports. So the final question is, can we use this knowledge to go beyond just predicting reactions? Could we become true molecular architects, designing and building brand new molecules with functions we can only just begin to imagine?